Okay, few fractographic pictures. Here we have experts. I don't feel like an expert in fractography. The cracks usually started in the ground material on the bottom here of the grinding groove, seem to be extended subcritically to a critical size, and then we have the catastrophic failure. I'm thinking that because we could not find any cracks using the bonded interface technique, two polished surfaces stick together and ground on the surface perpendicular to that. No cracks seen here, but we will typically see the side cracks from this was a biaxial test pellets for testing. In contrast, in the sandblasted samples, we were able to see these cracks, lateral cracks. They are not so detrimental to strength because they are more, perpendicular to the surface. They are not running directly into the material, and also the fracture origin always connected to that. Just few more recent results. I was interested, grain size, and there's not only the grain size. It's not only the pressure. I would like to see how important those variables in sandblasting really are. If you look at this picture, that was the sand was applied directly to the surface, so perpendicular to the surface. Here it was applied under an angle. So you see craters here, and you see these sharp scars, or in this case, and also this was I think 50 micron powder, and this one was 110 micron powder. So we intend to have a bit more systematic study on all those variables because they are so many times disputed, the influence of this and that, and I think we need to collect more data to know which variable is more important than from the other. The old results, extraction, we saw phase changes on the surface, but at that time, that method, which was the only one in the standard, we were not able to resolve to find any difference between the materials. Okay, but when we did it longer autoclaving, then we saw the big difference between the standard grade materials and the biomedical grade from Tosov, and we checked at the same time. I skipped that. And it's interesting when we check the sandblasted. The sandblasted material will transform a little more slowly than this one. So initially, sandblasting certainly hinders the aging. That were the first results. Also, with standard grade materials, we observed strength degradation after aging, while the strength degradation in this biomedical grade material, where the difference was certainly not statistically important. Okay, yeah. Okay, we checked the fracture surfaces, and you'll realize that's an overaged standard grade material with a very thick transformed layer, see? And the fracture started here, and that was kind of a delamination. So you, by aging, if nothing else, you will reduce the load-bearing area, okay? If nothing else. Okay, let's have a look now on on the fatigue behavior. We have chosen only one material, the coarse grained with a higher fracture toughness, and here are the strength and fracture toughness data. We applied same surface treatment, and we had another group which was sandblasted plus annealed for 1 hour, and the testing conditions were I think as before. So we divided those specimens into groups. They were either aged in artificial saliva for 1 day at 37 degrees C, or in 2 hours in an autoclave, or for 24 hours in an autoclave. The reason for these groups, sandblasted plus annealed, is that after 920 degrees C, the monoclinic that was after sandblasting on the surface will transform back to the tetragonal. Here are some XODs showing that after aging for 2 hours, we already, after accelerated aging at this sterilization temperature in an artificial saliva, we already have some monoclinic on the surface. So the pattern was also changed, but I'll not go into that. The important thing is, if we have a look, the sintered material was almost only tetragonal, and we already, after 1 day in body temperature, we got a small peak of the monoclinic fracture, goes up to 5% after 2 hours in autoclave, and 25% after 24 hours. Sandblasted, we started with a small amount of monoclinic, remained nearly unchanged under these conditions, goes up a little bit after 24 hours. Sandblasted plus annealed, we started with 1%, goes to 2, 3, and 9%. So the increment in the monoclinic here was the lowest. And in the ground material we also have a similar behavior than in the sandblasted one. Strength values, they were always a little bit lower if we have ground groups. Sandblasted were always a little bit higher. Sandblasted plus annealed were in the range of the controls. And if we look at the survival rate, we had 10 specimens per group. You'll see that we had the asintered material in air, the survival rate was 60%. They were loaded up to 60% of their strength, and after 1 million cycles, 6 out of 10 will survive, 4 will fail. And it dropped when we tested the material in water or in saliva. The survival rate of the ground specimens was dramatically reduced. Only 2 or 1 specimens, ground specimens, survived the testing in saliva. But you'll see here, none of the sandblasted specimens failed when tested in air. None when just exposed to water overnight or for 24 hours, a slight drop after autoclaving, and a lot scatter in values for the sandblasted plus annealed material. But the values will be somewhere between this control group and the sandblasted group. And if we put those things together, we always see the survival rate, how many cycles some of the specimens was able to survive. We always find the green on top. The green is sandblasted. And it's in most cases followed by sandblasted by this one, sandblasted and annealed. Then comes the control, and then is the ground material. Regardless whether that was tested in air or after accelerated aging. So if we calculate what would be the hazard rate in taking the controls as a reference, so if you have a sandblasted surface, you'll have only 20% chance, or the only 5 times less specimens are likely to fail during this 1 million cycles, and the survival rate of the ground specimens will be 3.5 times lower. And 0.5 means still much better chance for the survival of the sandblasted plus annealed specimens. And if we check the influence of the medium, I mean saliva, 24 hours body temperature, autoclave 2 hours, autoclave 24 hours, we see the hazard rate will be much for a failure will be larger than the controls, which means almost 2 times higher chance for a premature failure. So we put those things together into 2 graphs. The influence of the mechanical surface treatment as expected, considering the control group. Grinding is quite a bad operation. Sandblasting is a good one, so we'll have a heavy discussion afterwards, perhaps in that. Sandblasted plus annealed. And if we look the medium is considered here how long and under which conditions the material was exposed to artificial saliva. We'll see actually that 24 hours at 134 degrees in an autoclave has an impact. The short-term autoclaving has a little bit a lower impact, but let's say just for 24 hours, it's not enough to establish, to find any difference between the control material and those that were exposed to the aqueous environment. Okay, we can summarize that part. Grinding and sandblasting exert a counteracting effect on the strength and survival under static, and also on the survival rate under cyclic loading. Sandblasting is not bad, but it depends how it is done. And the distorted tetragonal zirconia on the sandblasted specimens hinders the aging. How much, what is the practical, let's say, result of this, we'll have to check. We don't know yet.